For clip note 33, we're going to be looking at extensions of the fundamental theorem of calculus. So for number 1 here, it says the FTC is an accumulation. So remember, when we integrate, we remove the rate. So oftentimes you integrate to find a change in something, a change in population or a change in an amount. So the integral by itself, just like what we have here and here, the integral by itself, if you find the antiderivative, that answer gives the total population or water or sand or traffic or anything like that, etc., between time A and time B. So this is just, if they're asking you to explain the meaning of an integral, is just a change in something, the change that occurred. Now, the fundamental theorem of calculus as a final position, integrate to find the end. So if you're interested in a certain position, we have to know what the initial condition was, and then we can add the change that occurred. So if you're talking about a location, we have to know where the particle started, and then add any change by integrating the velocity. Okay, and so this is just kind of, this equation right here is just the generic form of a total amount at the end of some requested time that you're looking for. Alright, so let's look at a couple examples that involve these formulas. Alright, so we got this little particle, and he's moving along the y-axis. So I guess that means he's just either going up or down. Up or down. So that, and we have the velocity equation for time values greater than or equal to 0. Given that S of t represents the position equation, the antiderivative, if you want to think about it that way, of velocity, given that the S of t is the position of the particle and that here's an initial condition, the guy started at 3, let's find out where he was 2 seconds later. So really it just depends upon what this graph is doing between 0 and 2, meaning if this graph is positive, then this little particle is just going straight up from 3. If the velocity is always negative between the time interval of 0 and 2, then this guy is dropping from 3. If there's a mixture of positive and negative values, kind of hard to tell unless you look at the area between the velocity graph and the x-axis to determine, did the particle travel more up? Because you have more of the graph that creates an area that's larger above the x-axis as opposed to below. All right, so let's do the setup according to the formula given ahead above us. So the position at 2 is going to be equal to the original position plus any change, and we're going to get that from integrating from 0 to 2, the velocity equation. Okay, and I could have just simply put in this equation right here. This is a good time to replace S of 0 with 3 if you want. Alright, so this is a good one to integrate by hand. I mean, if I had a calculator and it was, acceptable to use one, I'm certainly going to go and find this value by the necessary keystrokes. But for this one, I think we can find this answer by hand. So let's kind of see how that takes place. It's going to be u substitution. U will be the inside function t squared, and du will be 2t dt. And because t is present as a factor, we're in good shape. We can bring in the 2 and pull out the 1/2. I'm just going to go ahead and rearrange here and put sine t squared times, and I'm going to put the t behind, times t dt. And of course we know we can't multiply these two together. It's just for the convenience of putting it in this order so that I can use u substitution. Okay, I need to bring in a 2 to replace all of this with du, and then I need the 1/2 out here. Alright, so this gets replaced with u, and all of this is du. And so when we look at this, we've uncomplicated that complicated integrand, and now we know that the antiderivative for sine u is going to be negative cosine u. At this point, if you wanted to, like in the previous video, if you wanted to stay with the u variable and not go back to t, what you could do is you could change these limits right here from 0 to 2 to the u limits. And again, just to remind you, that would mean that when you plug 0 in for t, because it was originally a t limit, you would still get 0 as a lower limit. But when you plug in 2 for t, you're going to get 4. Okay. Otherwise, when I integrate, I'm going to have to replace my u with t squared. So we've been doing that, so we're most comfortable, I think, with that technique, so we'll just go ahead and continue with that. So 3 plus 1/2. The antiderivative is negative cosine u, so I'll put the cosine here, but I'm going to put the negative in front, evaluated from 0 to 2. Okay, so I need to replace the u with t squared, so I'll do that. If you can avoid some of these steps that I'm doing, that's fine. I just wouldn't probably do too many mathematical, things in one step. So 3 minus 1/2 cosine t squared 0 to 2. So cosine of 4 minus cosine of 0. Well, without a calculator, I couldn't tell you what cosine of 4 was, so I guess I'm going to have to leave my answer with cosine of 4. Perfectly fine. Cosine of 4 is exact. If you change it to a decimal, that's an approximate. All right, so this is going to be 3, and then I think I'll go ahead and distribute the minus here. So 3 minus 1/2 cosine 4, that becomes a plus, and cosine of 0 goes to 1, so that's just going to become a plus 1/2. So let's see, 3 plus 1/2, go ahead and combine those. That would mean that this was 6/2, because that's equal to 3, so collecting with another half would be 7/2. Minus 1/2 cosine of 4. Okay, and then you're fine there. That you're done. But if you wanted to rewrite it as a single fraction, just one fraction, your answer, you'd have 7 minus cosine of 4 on top. So let's take a look at example 2. Alright, so we have a piece of metal that's 8 centimeters long, and it's heated at one end. It's like you're sticking it in a fire. The function t prime of x, this linear function, gives the temperature in degrees Celsius of the wire x centimeters from the heated end. So this appears to be a rate of change. Okay, so the units would be degrees Celsius divided by over x centimeters. Which doesn't really make a lot of sense, but it is what it is. And for the rate of change, it's degrees Celsius per the x centimeters from the end that you're heating. All right, we're asked to find this answer right here and indicate units of measure, and then explain the meaning of the temperature of the wire. All right, so I'm going to go ahead and set up the integrand. T prime of x is 2x plus 3. So easy enough. I don't need to get anything ready for integration. This goes back to x squared plus 3x. And we're going to evaluate that from 0 to 8. 8 squared. Okay, that's 64 plus 3 times 8 is 24. So 64 plus 24. And love those zeros when everything has an x in it. Every term has an x because that's just 0. So that looks like 88. Indicate units of measure. Well, remember what it said up in the note card at the top. It says integrate a rate, lose the rate. Well, this is a rate right here, so we're going to lose the x centimeters. So it's 88 degrees Celsius. All right, now let's explain the meaning of the temperature of the wire. All right, well, thinking about what was said earlier, this represents a change in the temperature from the heated end to the opposite end in degrees Celsius. So kind of remember that saying nuts. Let's do the number, the units, the time, but in this case, kind of interesting, there's no time. Instead, we're talking about a length. Okay, it's the x here instead, and then we're going to use a sentence. All right, so there it is. 88 degrees Celsius means the change in the temperature of the wire in degrees Celsius from x equals 0, the heated end, to the opposite end, to x equals 8 centimeters. So again, think of that acronym NUTS. We've got the number here. I have the units of that number. I have the time, but like I said, in this case, that's going to be your independent or your limits, but instead of time, it's going to be x, the length of the wire, and then we have the sentence. All right, so this is just putting the FTC into practice in context with just different problem situations. All right, we're going to take a look at next note card number 22. So if you want to take the time to flip back to number 22, I'll join you there in just a second.